Hello. Welcome to another
Welcome,
episode of
everybody.
Let's Talk.
It's good to see you, Andreas, and good to see you moving.
This is
let's
our
let's
third
hope it
attempt
keep
to
moving.
our fourth episode in robotics.
Yes, and sorry, I'm a bit in a weird state because I think this is the third time we're trying this now.
It
We had
is.
a failed live stream with audio issues. Then we had some awesome issues with maybe my macOS and GoPro and whatever. And now I just restarted, and we're off to a good start here. So I'm
Nevertheless,
monitoring you,
Sven,
Andreas, and hope
yeah,
you're keeping moving. So
I'll keep waving like those winking cats
anyway,
you see at chaos events. Remember
yeah,
those?
yeah.
No, I won't keep doing that. I won't annoy everybody. Sven,
Anyway,
this is our
this is
fourth
our
episode
exactly.
in robotics. Do you remember who else we spoke to?
Oh, a
What other
little
guests?
test at the beginning, right? So yes, I think I do actually. We first talked to Alona von Devantro, and we kind of explored how robotics and care basically goes together. It's quite interesting, really, to see also these videos of the robot moving inside of an elderly person's home, for example, and what it's able to do and whatnot. Then we talked to Kuka, which was really quite cool. So that was I think more an industrial focus. And also we discussed actually how these robots collaboratively work together and what knowledge is.
How those can be programmed and all of that. That there's choreography has been a quick thing, and all the knowledge that's necessary to
Kuka programming language, how to program a robot actually. So I'm still not an expert, but maybe ChatGPT can help at some point. And then we had an amazing episode with Reply, right?
With René Schulte.
Exactly. And we saw a lot of videos of humanoid robots, I think. We focused on humanoid robots, although we've also seen Spot walking around, but we focused on Amica, for example, and other robots. So that kind of did bring the humanness back to robotics, I believe. And now we have a fourth episode, and we have Oliver Hausdörfer here waiting to be let in, actually. And he's from the TU Munich. And we're going to focus a lot on I would say, research, take a more scientific route. We also have some exciting drone videos and choreographies, and I'm excited.
It's going to be awesome. So welcome, Oliver, on stage.
Here we go.
Hi, welcome. Oliver.
Hello, Andreas. Hi, Sven. Thanks so much for having me.
How are you? Thank you for coming back, to be honest with you.
Sure, no problem.
Oliver, so why don't you tell us a little bit, actually, what you maybe do at the TU Munich, who you are to start with?
Sure. So I'm a PhD student at the Learning Systems and Robotics Lab, and I try to work with robots that can learn in the real world and, to make robots more applicable to everyday scenarios and, work towards robots that you might encounter in your everyday life. And I do so using tools from robotics and tools from machine learning. And before I joined as a PhD, I have a background in mechatronics, robotics, and mechanical engineering.
Oliver, just a quick question now that you're our fourth guest already. We spoke to a couple of others that are in the industry already that do build robotic applications. How is that research that you're doing and that research for real world applications? Give us an example of what's different and what's the typical application for this real world learning that you're researching compared to the others we spoke to.
Yes, that's a good point. So I believe you mentioned you talked to a roboticist from KUKA, and I mean KUKA is famous for their industrial robots, and these robots do a really good job in industrial applications. And usually what you have in industrial settings, you have a defined scenario, a defined task, and then you can program your robot to perform at this specific task really well. So this is a problem. I will be careful with this formulation, but that might be considered solved. And now challenges in research, or one of the main challenges in research, is how can we achieve more generalizable robot skills and, you know, make robots more applicable for a wide range of applications. So one thing to think about would be, you put a robot in a kitchen, you know, everyone had a great dinner party, so then you just tell the robot, okay, please help me clean the kitchen, you know, and then you have all those high-level task understanding skills from, okay, I need to clean the table, I need to put the things in the dishwasher, and beyond this high-level reasoning, to be able to execute those skills in a very unstructured environment. And I would say this is one of the
Yeah, I can totally imagine that part. I do have one of those vacuum robots around here, and that like half of the time doesn't find its way home.
And I mean, just for everybody to understand a bit what we're dealing with here, basically, and what kind of research you're doing, I just pulled that link and shared that link, basically, latent action priors from a single gate cycle demonstration. And we joked about it earlier, right? So I still understand nothing, but I can look at the images here and I see there's a spot-like robot that's learning to walk, I believe, right? And so those are the real world things that you're dealing with, right? Helping a robot to move around, maybe grab some objects and, I don't know, open a fridge and stuff like that, right? Quite cool stuff.
Yeah, I mean, you're getting right into the research here. So the idea of this project is, as I said, if you want to solve a wide range of tasks, and you use machine learning, you usually need a variety of data. And data is really hard to come by in robotics. So what you do is you use simulators that can generate the data, but this comes with a problem. So, I mean, a simulator is not a perfect reflection of the real world. So the data you see is different from what you encounter in the real world. And then your solutions that you get for robotics, in this case for walking a quadruped, will be different than what you would expect to encounter in the real world. And so the question of this paper is, how can we still leverage simulation, but at the same time get realistic solutions, in that case, locomotion, like gates.
Well, when I'm looking at all of that, and when you explain how you're using simulation, that immediately raises a question for me, like, what is actually possible? You are researching that in a simulation. You must be aware of the limits and the boundaries. Can you talk a little bit about what is possible with that simulation approach, and beyond that, eventually also about the limitations, what's not possible in that setting?
That's a really good question, and also quite a hot topic. Let's start with the what you can do side. So there was a lot going on in the direction of GPU, so graphic card accelerated simulation and training. So what you can generally do, you can generate big amount of data really well. And there are some techniques that bring the simulation quite close to the real world, although there will always be a gap. We call this the simulation to reality gap, and that's always challenging. One big limitation is you saw the videos from the simulation and they look different to the real world. So if you want to obtain vision-based policies, so if you want to go from a camera input to a robot action, that's usually not possible to train in simulation, because as you saw, like, the images you get are completely different from what you would see in the real world. So typically in the simulation, you train so-called state-based policies. So you use non-vision inputs to get your behavior. Then you put it on a real robot and you kind of replay what you learned in simulation. At the same time, you record the image video, and then you have like a student-teacher learning approach to mimic the policy learned in simulation.
Just to go a bit sideways, maybe my approach to visual and simulations is probably more from the gaming side of it. If I look at say modern AAA type of games, there's a lot more of physics engine and visual representation that we had in that paper. But ultimately, if I interpret that, that's just a question of how much simulation you throw at a model to simulate another model. Is that about the right angle to look at it? Like how you invest your simulation resources?
Yes, of course, you can try to scale up your compute and make the simulation more realistic. Though I think it's quite established in the community that it is not possible to like completely simulate the real world. Like the real world is not entirely deterministic. It's really hard to capture all the nuances of reality, like all the textures of objects, all the reflections of light in the glass. This is like so nuanced and so expensive to simulate that I assume there are some limitations, and usually you don't go that far.
Okay, interesting.
So speaking of other real world applications, you also gave us a really cool link to a drone video that I think maybe we could come to next. And maybe we should first take a look at the video and then discuss actually, right? So, but it's basically a drone and many drones moving around in a choreographed way to music, right? So it's pretty fascinating. We try to find it and then maybe first look at it.
Sure, let's have a look.
Perfect. With music, so here we go. So that is pretty fascinating, I must say. Maybe we can just restart it without sound, though. I guess you can hear me, just so we can watch it one more time. So all these movements have been calculated by one of your systems, I guess, right? And so that means you must have been doing this for many drones, and they must somehow be working together. Tell us more about that. What's happening here?
That's correct. So maybe to draw the bigger picture, the idea of the project is that previously, if you want to design drone choreographies for shows or for big events, you need a technically skilled designer who can design all the waypoints of all the single drones. And the idea of this project is that you can offload this work to large language models because they have this implicit word knowledge, and as we showed, they are able to design different patterns that can move meaningfully synchronized with the music. So we give an input to a stock large language model, and I think in this case it's ChatGPT, and ChatGPT then generates the waypoints that the drones follow.
So the goal really is to create a system that does automate this choreography. So you're optimizing the manual effort to make sure the drones move in a way they don't hit each other, and to literally automate that. That's the goal of the project, right?
Exactly. So as we saw, the choreography that you saw was entirely generated by a language model, and it's a really good first shot. So there's no human design. And of course, you can decide to iterate on that. Like you can reprompt the model. You can say, okay, make this more dynamic and so on. And you can also adjust this with a human engineer. But the general idea is to, the high-level design, do this by the LLM. And then, of course, what you need is some safety layers, because language models, they have an abstract understanding of what the choreography is, but they don't have an understanding of the specific model dynamics of the drone. So what I mean by that is the language model could tell the drone, okay, go from here to here in 0.5 seconds, which might look very nice and might be fitting to the music, but it's dynamically not achievable. So one contribution...
So the drone may be too slow to achieve that or something
for instance.
Okay.
So one of the contributions of my colleagues in the lab was to introduce a safety filter that basically makes sure that the trajectories can be followed by the drone, for instance, with the acceleration, and that no drones collide.
That's exactly the point I wanted to raise. Otherwise, you would basically have, let's say, 25 paths for drones that could potentially collide, right? So that is an extra layer that makes sure that this doesn't happen, and then recalculates the flight paths or so. Otherwise, you would have a lot of broken drones, I guess.
Exactly. So some colleagues at the lab who developed this project have a strong background in those safety aspects, because if you want to do robotics for the real world, it's always important to think about, potentially safety aspects and hazard and damages. So they implemented this kind of safety layer to make sure that, no collisions happen and the paths are feasible.
On the way there, allow me that question: how many times did that safety layer fail on the way to that video?
How many
drones really crashed
into safety layer?
So I think my colleagues are really gentle with the drones, so not too many drones, crashed. And
I just come up with another spontaneous question. So let's assume we have a huge event somewhere in the Olympia Park in Munich or so with thousands of drones. How many drones would we find on the ground afterwards? Is it so perfect that we get 0 drones, or is this still happening? It's kind of
I think that's a good question. So we are aware of the limitations. So to mention one, so currently, like, you define a safety zone around the drone, and currently, due to computational reasons, this safety zone is an ellipsoid around the drone. But below the drone, you have a cone of air moving because of the propellers. So it's actually not an ellipsoid; it's more like a cone. So if you have 2 drones flying below each other, the ellipsoids might not collide, but you have this aerodynamic influences, and there sometimes we see crashes. So if you want to get 0 crashes, you put more money in the project to improve the shape of safety, and then I'm confident people at Olympia Park will be fascinated.
Yeah. And I mean, just before we, sorry, it's to interrupt, Andreas, but before we start the recording, you also told me that you will get busy again because someone is requesting a Christmas tree with drones, basically a new Christmas animation. So that brings up the topic for me also. There is a commercial application of this, right? I mean, I can well imagine that big events would pay money for having you calculate their drone path, basically, to bring up a nice show, for example, right?
True. So first, I encourage everyone to stay tuned for our awesome Christmas videos that will come out. And yes, there are commercial applications. So this was not at our chair, but at the chair where my current supervisor did her PhD. There was a startup that used the technology, and they brought drone shows to a Broadway show, and I think they performed with Lady Gaga, so at huge, music concerts. And I mean, it's a great effect for people to see. So I think the commercial applications might only increase.
Okay, but there is, in a nutshell, there is commercial applications. So all of this is, and events being the main use case for that. Are there other commercial applications?
So for the choreographies, I believe that shows are the main use case. For the general idea of having language models steer drones, I mean, it's still an early technology. There is development to be done. It's not yet, fully commercialized. But there might be a wide range of applications. I don't know if you think about monitoring biodiversity in forests, which is a popular application for drones. And you can tell the drone, move to that tree, and then the LLM generates the path. Would be much more user-friendly than, needing to steer it.
To make interaction with any type of robot, not just drones, probably more easy and more accessible, so to say. Okay, that's possibly the next area or topic we can talk about. You told us that's robotic foundation models. That's the name of the technology to research, and its goal is to make interaction with robots more accessible. But tell us a little bit, how does that work, and how does artificial intelligence play a role in that sector?
Yeah, so I mean, you captured one of the essences, which is interacting with robots in more natural ways, such as human language or pictures. And so the general idea of those foundation models is maybe going a small step back towards language models. So what we saw in language models is that you just naively increase the model size and you naively increase the compute and the training data that you train on. Your models hugely increase in performance. And now the same thing is, we try to do in robotics, or that actually is being done, that you record. I think the biggest data sets currently have around 80,000 hours of, robot interaction. You take all this data, you train a large model, and then you deploy it to a new use case, and you kind of hope that we call this like within distribution. So you hope that the new task that you see is somewhat of an interpolation of all the other tasks that you've seen. And the results showed that, those models beat existing benchmarks and that it works really well. So
in other terms, what you're doing with those type of models, it's not like the large language models that everybody is talking about for the past 2 years, but it's really like movement models where you train artificial neural network how to touch things. Is that about what you're saying?
So usually the input to those models is language or a goal image. So you give a picture of the scene, how it should look like. And the output is, if you look at the manipulator, it's usually delta and effector positions or poses. So yes, you go directly from language to robot actions.
I think in one of the past recordings, I don't remember which one it was actually, but you told us about Lego, right? Wasn't there like a kind of, you take a picture of a Lego house, and then the robot in the end has to build it, right? That's one of the tasks that would become possible, I believe.
Yeah, that's a project our lab is quite excited about, because it has all those aspects, right? It has really long horizon tasks. So going from small blocks to fully assembled complex structures. It's highly interactive. You have many contacts. It's nice to interact with the robot, have human feedback, have like language feedback, and so on. Yeah, so that's one use case we're working on.
Very cool. And just before, actually, when we talked about the drones, to be honest with you, I also thought a bit about ants, right? And like how ants, for example, collaboratively work together to achieve one goal. And that is it's a bit similar, right? Because you have all these drones completing one task, and I could imagine, like with these autonomous robots, maybe they also could kind of work together to bring in the fastest possible way something from over there to over here, basically, right? So that sounds like a similar application, for example, right? Like that could be solved with your technology, I believe. Is that roughly correct?
That's a really, really interesting comparison. And so I hope I'm not going too much off track, but I would almost believe that's kind of an inverse approach. So usually what you see in ants is, so the effect is called emergence, right? You have many agents that have very simple rules. So the rule is always have a distance of 1 centimeter to your neighbor, or follow the smell to the food. And based on those simple rules, you have emergence of complex behaviors to achieve complex tasks.
Yeah.
And we also achieve complex tasks, but the approach is the other way around. So we use a large language model that kind of has the overarching knowledge, and then it distributes subtasks.
That's really interesting. Yeah, I realize it now. So
so
you basically have one central intelligence that tries to coordinate everything versus individually thinking items, more or less. Yeah. So
And this is a really good question in robotics, because both applications are valid. And usually we talk about this in explicit versus implicit skill discovery. So do you take many data and you train a centralized agent that distributes tasks? This is one approach. And the second approach would be explicit skills. So you define like small pieces of skills, and then you deploy them decentralized, and you hope that you get kind of an emergent behavior. So it's not fully clear what is the best.
And I just realized it's a bit philosophical. It's like, do you believe in God, basically, right? Is there one truth that can be distributed? So, sorry, it's getting too far. But I think it leads us to the next question, right? Like this general intelligence, AGI, basically, right? Do you think this will at some point happen, that we will see humanoid robots that are basically behaving like a human being and are able to do the tasks that we can do? Is that something that's on the horizon?
Or to add to that question, a debate I had with a professor from a technical university was more on the theoretical side of things. And one of the arguments that was floating around the discussion was that like those chat type of large language models, they wouldn't have all the understanding, all the meaning to become general intelligent. But now that you're telling us that there is not just language, but also visual feedback, tangible feedback, would that lead us there to bring all those inputs and meanings together? So that's something that leads to artificial general intelligence?
Yes, so maybe to merge your points, like the both you both made, I think the community agrees that you need different modalities to get what we usually imagine as being, AGI. So you need a physical understanding of the world, as you said. You need tactile sensing and so on. And the only way, or pretty much the only way to get this, is through robot interaction with the environment, or to some degree human interaction. And humanoids are, they're pretty hot right now. They're really versatile. The big advantage is you can take any existing shop floor or any existing setting that's like suitable for a human, and you can just put a humanoid robot. And it's, in the short term, it's impressive to develop these technologies, and it's definitely useful to collect all the data. The question is, will it in the long term really be the most efficient solution? Because if we design a technical system anyway, we could just make it in some sense, better than a human. So who tells us that 2 arms is, the best way to do things? So I'm not entirely sure if humanoids are the best solution, but at the moment it's,
like you're not entirely sure if the human system is perfect for this planet.
The human shape would give it the best acceptance, probably. Like just trying to imagine what you're thinking of. Like, what would the robot look like? And if I look at that, would I really want to
Before you answer, it
that?
reminds me a bit of René, right? We talked a bit with René, for example, in one of the last shows. Why are they actually humanoid robots? That's because humans did the task first, and now we want to have machines take over, right? That's why the machines need to look like humans, so they're able to do similar tasks, for example. If you would start from a different point of view, basically, right, with a different machine, or so that's maybe made for another robot or so, we would have different looking robots. So
and you always have the proof of existence, right? So we know that a human can do it. So if we build something like a human, we kind of know that it can achieve the task. But one thing from the top of my head is, legs are quite inefficient if you want to move at high speeds for distance. So you could just put wheels, right? So bipedal walking is very versatile and desirable in many scenarios. But so you saw the video of the quadruped, and I think in the future we'll see quadruped with wheels. It's much more efficient than to walk, and much easier from a control perspective.
Very interesting.
Let's maybe wrap this up a little bit, Oliver. You're doing all this research. You're really on the edge of research. You probably have a pretty good idea of where all of this is going. Maybe give us a little bit of a glimpse into what's going to happen.
So we will see more diverse robots. I think that is for sure. That are easier to interact with. I'm not aware of any commercial applications, but we see really good progress in the scientific community. So I think within the next, 5 to 10 years, there will be huge progress. Hardware-wise, you mentioned the humanoids. We saw the quadrupeds, so they will definitely become cheaper. So one thing that still is a challenge is like dexterous manipulation with hands. So for instance, hands are for one robot hand you can pay more than for a whole humanoid, because it's so such small parts and such an intricate design. So huge advancements will be made there to to get the price down. And of course, tactile sensing is a big challenge, and we hope to see advancements.
Very cool.
Awesome. Lots of stuff coming. Thank you for all your insights, Oliver.
Really appreciate it.
It was really great having you. Thanks everybody for watching. So I hope this time we have the good quality video and audio. We'll know it in a few seconds. Hit the subscribe button. Thank you so much. Bye-bye.
See you soon.
Talk soon.
Ciao.
Thank you.